Alright, so in this video I'm going to go over how to complete a problem that involves circular wavefronts and point sources. So before we do interference in 2 dimensions and talk about constructive and destructive interference, let's first talk about constructive and destructive interference in 1D. So when we have a wave that adds with another wave, where a crest, I know this may seem like review, but I think it's definitely worth going over. Crest plus trough. You guys already know what we're going to get. When one wave meets another wave, crest to crest, we're going to get a really big wave. Right? Crest, trough. Amplitude plus 1 minus minus, we're going to get 2 plus 2 minus, right? This is called constructive interference. And this will produce an antinode, right? This will produce an amplitude, a large amplitude here and a large amplitude here. This is what we call an antinode, right? Now on the flip side, if we have a crest from one wave that meets the trough of another wave, and a trough of that first wave that meets the crest of another wave, we're going to have something slightly different. You guys already know we're going to have destructive interference. Minus plus, what's it going to look like? Flat line, right? You're going to have plus 1, minus 1, minus 1, plus 1. You're going to have no displacement, right? So 0. This is called destructive interference. And this is going to produce a node. Right? No displacement. No displacement. Alright, yeah. Word. So now we have some review of constructive and deconstructive interference. Now, how the devil does that apply to what we're going to do in this problem? Well, it applies because we're going to do something called a path difference analysis. A, P, D, A. As it were. Let's see how that's useful here. Basically, we need to figure out for each of these points, A, B, C, D, and E, whether or not the waves from point source 1 and 2, I'm going to label these 1 and 2, are interfering constructively or destructively. And the way that we can do this is figure out the difference between the waves that are propagating from point source 1 and point source 2, the difference between their positions at each point A, B, C, D, and E. So we basically know that there's going to be one wave that comes out from point source 1 with a wavelength of 2 boxes lengths. So let's say one wavelength is equal to 2 boxes. Then, so half a wavelength is equal to 1 box. Cool. Now, we also know that another wave is going to be generated instantly from point source 2 that also has a wave crest. They're releasing waves simultaneously in phase. And so we want to figure out what happens. And so we can do something called path difference analysis. So I'm not writing down the answer to this question. I'm just showing work that'll help me figure out for all of the point sources, or all of the positions A, B, C, D, and E, whether or not there's going to be constructive or destructive interference. So what I'll do is actually just put a line right there. So for path difference for A, I'm going to write it like this, PDA. I want to look at the difference between, or the distance between point source 1 and position A. So we'll call that source 1A. We're going to look at the difference between point source 1 and A and point source 2 and A. We're going to look at the difference between the waves that arrive from each of the point sources. So we have source 1A minus source 2A is equal to 1 wavelength. How do we know that? Because this is 2 boxes, that's 1 wavelength. Minus, from point source 2, we got 1, 2, 3, 4 boxes, that's 2 wavelengths. Alright, so the difference is minus 1 wavelength. I need to move this over somewhere. I'm going to hold up and then we're going to do all these and we'll find a pattern. So from source 1, that is 1 box, or half a wavelength, away. From source 2, it is 1, 2, 3 boxes, 3 halves wavelengths away. The difference here is still negative 2 over 2, so negative 1 wavelength. For C, that is half of a box, so that's 1/4 of a wavelength. So source 1C minus source 2C is equal to 1/4 of a wavelength minus, from point source 2, that's 1, 2, 3 fourths of a wavelength. That's 3.5 boxes. So we'll call it 3/4 wavelength. If you want to see a breakdown of why this is the case, let's do a little conversion real quick. So if 1/2 of a wavelength, if 1 box is 1/2 of a wavelength, then from point source 2 to C we have half a box, or 1 box and then a half of a box. So we have 3/2 box. Now if each box is 1/2 wavelength, then let's do a little bit of a unit conversion here. So 1 box, 1/2 wavelength per box or whatever, so then we get 3/4 wavelengths per box, 1/2 wavelength per box, yeah. So then we get 3/4 wavelength. Right, so 3/2 box, for every half a wavelength that's 1 box, we get 3/4 wavelength. Alright, PD, source 1D minus source 2D is equal to point source 1 to D, that's 1, 2, 3.5 boxes. So again, that's just going to be, oh no, this is slightly, not 3.5 boxes, that's lol. This is 1.5 boxes. 3.5 boxes would be 3 1/2, which is equal to 7/2 boxes. And so from point source 1 to D, that's 1, 2, 3.5 boxes, or 7/2 boxes, and then 1/2 wavelength per box gives us 7/4 wavelengths. And then minus, from point source 2 to D, that's the same one as before, so minus 3/4 wavelength. That's 1/4, 2/4, 3/4. So that's 2 wavelengths, so because it's 7 minus 3 is 1. And then finally, PDE. All we're doing is finding the distance between each point source and the box. S1E, 1, 2, 3, 4, 5, and 5 boxes, so 5/2 wavelength, minus 1, 2, 3, 3 boxes, so 3/2 wavelength, and that gives us a total of 2/2 wavelength, or 1 wavelength. Wait, 7/4 minus 0/4, that should be 4/4, or 1 wavelength. Yep, that's incorrect. Oops. Alright, so let's see if we can find a general trend here. We see that there are 1, 2, 3, 4 points here that see a whole number integer, where a whole number integer difference between the wave from point source 1 and the wave from point source 2. So these two the waves from point source 1 and point source 2 are occurring exactly 1 wavelength apart. There's a difference of exactly 1 wavelength, or negative 1 wavelength. Now that's true at point A, point B, point D, and point E. Okay. Now at point C, the wavelengths the waves are occurring half a wavelength apart. So they're arriving at this. They're arriving from both these point sources, 1 and 2, at point source C, exactly half a wavelength apart. Now let's go back at our path difference analysis, see what that even means. So if two waves are arriving at exactly one wavelength apart, that means that it doesn't really matter whether or not this is one wave or two waves or three waves or four waves. Like, two waves are going to be arriving, and the crests from both of the waves are going to be meeting if they're arriving exactly one wavelength apart. Because if they're arriving one wavelength apart, that means a crest from point source 1 will be meeting a crest from point source 2. And they're exactly one wavelength apart, that's going to be the case. So that every time you have a whole number, you know you're going to have crest meets crest. Now if you have half of a wave, that means that this is one full wavelength and this is half a wavelength. This means that the two waves are going to be arriving half of a wavelength apart. So the crest of one wave, maybe from point source 1, will be meeting the trough of the wave from point source 2. And so what you're going to have is destructive interference here. Okay, so a good rule of thumb is that whenever you have, I'll put this down right over here. A good rule of thumb is that once you find the path difference PD is equal to plus or minus 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, whatever integer, if they're occurring integers apart, then this means you have constructive interference. The crest from one point source meets the crest from another point source, and you have constructive interference. Right? And you have the formation of an antinode. Now, if the path difference is equal to pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, any odd number, you're going to have destructive interference. Or any half integer, rather. Because that means that the crest from one wave is meeting the trough of another wave. Okay? So crest to crest is a full wavelength. Crest to trough is a half of a wavelength. One wave from point source 1 is meeting a wave from point source 2 exactly half a wavelength apart. So if this is one full wavelength, this is another. This is a full wavelength right here. Now they're meeting at exactly one full wave apart. That means that here they're going to have crest to crest. They're meeting half a wavelength apart. Here you're going to have crest to trough. Right? I hope that makes sense. This is still kind of a tricky concept. Let me know how the problems go. You should try and finish up using the same process. This problem right here, it's just very similar. Just set it up in the same way. Find the differences between the point source, between point source 1 and 2 at A, B, D, E, C, and F. Do the same thing for the two problems or the two tasks that are like this in your wave motion model pack. Okay. Let me know if you have any questions.